Yo, what's up, guys? Welcome back to another video. Today we're going to be talking about a little rule in calculus. It's called L'Hopital's rule. It helps us with many limits, and it's a way to get a legal answer from an illegal answer. Also, Happy New Year's, Happy Christmas, Happy Holidays, whatever y'all celebrate. It's been a minute. I've been on holiday. It's been a long time, but I'm back. So let's get right into it. This is what L'Hopital's rule states. It essentially states that if we have a limit as x approaches some type of number c, and we have it in the structure of a function as f of x over g of x, if these two functions somehow turn out to be 0 over 0 or infinity over infinity, then L'Hopital's rule states that this limit as x approaches some number c can be rewritten as the same limit, only f of x and g of x turn into the derivative counterparts, f prime of x and g prime of x. So without further ado, let's take a look at this in action. So a famous example of L'Hopital's rule that we can use is the sine function. We essentially have the limit as x approaches 0 of sine of x over x. And remember what we said about L'Hopital's rule. It either has to be in the form of 0 over 0 or infinity over infinity. Those are called our indeterminate terms. Just remember that. So we have limit as x approaches 0 of sine of x over x. The rule of thumb for any limit problem is to always plug in the number, no matter what happens. So we plug in sine of 0, which is 0. Then we plug in x for 0, which is 0. We see that we do have an indeterminate form, so therefore we can use L'Hopital's rule. So essentially in AB or in BC calculus in high school, the way to answer one of these questions and the free response is by saying, by L'Hopital's rule, and this wouldn't be equals, this would be arrows, because you're not saying that it equals 0 over 0, it just says it turns into 0 over 0. But essentially, you write by L'Hopital's rule, this is just shorthand, limit as x approaches 0 of sine of x over x is equal to limit as x approaches 0, sine of x derivative is cosine x over the derivative of x, which is 1. Once we plug everything in, we get an actual answer of 1. And this is the way how we go from an indeterminate illegal answer of 0 over 0 to an actual answer in 1. This is famous. I don't know why. I think it's a squeeze theorem. But it's just famous for some reason. I don't really know for real. I don't know. I just do the math. This is another famous example. We have limit as x approaches infinity of x squared over e to the x. From here, we plug infinity to both of these numbers. We find out that they turn out to be soon infinity over infinity. So what I'm going to do is I'm just going to do this equals and then this L, because that's how you do it in college calculus. Essentially, we're going to take L'Hopital's rule this way. So we're going to do limit as x approaches infinity again. So we do 2x over e to the x. The derivative of e to the x, if you remember, is always just e to the x. So essentially, you might find a pattern and you might find that we plug in infinity to both of these functions again, you get the same thing of infinity over infinity. What do? You just do it again. This time, the derivative of 2x is just 2 over e to the x. And you see here that we finally have a function that we can plug it into. We know that the limit as x approaches infinity for 2 is just 2, and for e to the x is infinity. So it's basically just 2 over infinity. However, we know that anything a constant over a hilariously huge number such as infinity is always going to be 0 because it's bottom heavy. And that's essentially what the limit goes to. So the limit as x approaches infinity of x squared over e to the x is just 0. Now we're going to go into a very, very famous example. This is one you should prepare for. We have the limit as x approaches 0 from the right side of x times the natural log of x. You might think that we might not be able to use L'Hopital's due to the fact that we don't have a function in a fraction form. And let me get into it. If we plug in limit as x approaches 0 for x, we get 0 times natural log of 0. However, because of the graph of natural log, you have to remember that natural log never truly touches 0. It always just approaches it. We see here that as x approaches 0 for natural log, it just goes into negative infinity. So essentially, this is an indeterminate form where we have to solve this limit by rewriting the question. It sounds complicated. It's not as difficult as it sounds. And this is also called one of the 7 deadly sins of mathematics. How do you rewrite this question? Well, you have to remember that you can rewrite x as a different way. We can rewrite this as doing x is equal to 1 over x. The reason why this works is because if you have 1 over x, you can do keep change flip. So you keep the 1, change the 1 over x to become x over 1, and then keep change flip, and that's what you do. And that's what we're going to do with this limit. Shit, that's supposed to be next. Don't mind my cussing. Now, finally, we're able to use a form that everybody's known. The natural log, as it approaches 0 from the right side, is going to be negative infinity. And 0 approaching from the right side of 1 over x is going to be just infinity. The reason why that is because let's take a look at the graph of 1 over x. We see from the right side, it's just approaching infinity, and that's what it is. But it also makes sense because let's say you had 1 over 0.1, which is equal to 10, and then 1 over 0.01, which is equal to 100. Whenever a constant is divided by a hilariously huge number, not a hilariously huge number, by a really, really small number, really approaching 0, it's always going to be infinity. So essentially, now that we have one of the indeterminate forms in order to rewrite this, we can do L'Hopital's rule and do limit as x approaches 0 from the right side of the derivative of natural log of x, which is just 1 over x, over negative 1 over x squared, which is the derivative of 1 over x. Essentially, now we can just rewrite this form to be 1 over x times negative x squared using keep change flip. Essentially, we get limit as x approaches 0 from the right side of negative x, which in turn just becomes 0. And that's exactly how you rewrite a limit in order to make it work for you. Now we're going to do a very, very famous example of L'Hopital's. I think this one might be difficult for some of you. It was difficult for me especially because I had to wrap my hand around this. But let's take a look at this. The last example I'm going to do is limit as x approaches infinity of 1 plus 1 over x. And you're going to see why it's very, very famous. Once we plug in infinity for all the x's, we turn out that this is also another indeterminate form where we have to rewrite the question. This is 1 to infinity. You might think that 1 to the infinity is just 1 because 1 to the anything power is just 1. However, I think in real analysis or something like that, you learn that it's really not, or even in calculus, but It's just indeterminate. I don't know why. Don't ask me. I don't know for real. But like anyway, we have limit as x approaches infinity, 1 plus 1 over x to the x. You might be wondering to yourself, how can we rewrite this into a way where we can use L'Hopital's? Here's how. We just have to let this function be y. And from here, we can use the rule of logarithms. So we can use log base e, aka also known as natural log. And the rule of logarithms states that if you have a natural log with an exponent, you can bring down that exponent and bring it to the front, which is what we did here. So now from here, we can finally do the limit as x approaches infinity of x natural log 1 plus 1 over x. And you might be wondering to yourself, well, we just have another indeterminate form. This time we have infinity times 0. And you're right. But we're going to do the same thing we did in the last question. And we're going to rewrite this question to be natural log of 1 plus 1 over x all over 1 over x. Now from here, we get the indeterminate form of 0 over 0. And so by L'Hopital's rule, and the reason why we get 0 over 0 is because once you plug in everything, natural log of 1 plus 1 over x, plug in infinity, natural log of 1, which is equal to 0. Limit as x approaches infinity of 1 over x just turns into 0 again. So by L'Hopital's rule, you're going to see that once we take the derivative, we're going to have some very, very different things. So we have natural log of 1 plus 1 over x, which for the derivative is negative 1 over x squared all over 1 plus 1 over x. Then we take the derivative of 1 over x, which is just negative 1 over x squared. And you can see actually that we can cancel out these terms because they're the same. So from here, limit as x approaches infinity of 1 plus 1 over x. From here, what you can do is you can just plug it in like normal. I'm sorry, I forgot the 1. I forgot that once you cancel everything, it just turns to a 1. So essentially, you have limit as x approaches infinity of 1 over 1 plus 1 over x. And then from here, what you do is this just turns into 0. So you essentially have 1. But we're not done. We're not done. I repeat, we are not done. Because if you remember, I turned y into natural... Oh, what did I do there? I turned y into natural log of y. But that's the limit as x approaches natural log of y. Because I let this be y. So how do we turn it back to the actual answer? Well, since we know that natural log of y as limit x approaches infinity of natural log of y of this function is equal to 1, what we can do here is, in order to turn it back into just y, since it's a natural log and it's logarithmic, we just do the opposite and we do, what's it called? Power. I think it's called power. Yeah, you just do the power, which is e, and then it cancels out. And so then we see that e raised to the first power is just equal to e. So therefore, limit as x approaches infinity of 1 plus 1 over x to the x is just equal to e. And fun fact, this is actually how we get the number e. That's why it's irrational. I think this is in terms of banking. I think this is in terms of banking. Banking, finance, you'll find this in compound interest. Very, very useful when you're talking about money. I learned about that in business. But that's essentially how L'Hopital's rule is used. It looks complicated. I promise you it's not. It's just a bunch of math, and you just have to do it a lot of times in order to really feel it, really get into it. However, this has been L'Hopital's rule. Again, it's been a minute. I apologize for that. I've been on holiday. It's been very, very difficult. I've just been stressing out. I'm so stressed out. I don't know when the next video is coming out. But hopefully y'all enjoyed this. Leave a like, share, subscribe, please. I'm really, really broke. I'm a broke college student. I kind of need the funds. Thank you for watching, and hopefully you have a new year.